All right, let's jump right in. Welcome, everyone. I am absolutely thrilled to have you here for this explainer. Look, if you're an engineer, a procurement specialist, or a project manager working anywhere in the UK's industrial sector, you already know the deal. Material selection, it can literally make or break a project. So today, we're focusing on an absolute workhorse of modern engineering, and that is titanium grade 2. We're going to dive in and break down exactly why this specific grade has become the definitive go-to material for UK industry, really bridging that gap between high-end material science and real-world supply chain economics.
So, here's our roadmap for today. We'll start by defining the Grade 2 standard, then move into key technical specifications, look at material grade comparisons, explore some major industrial applications, and we'll finish up with the practical side, UK procurement and pricing.
Okay, part 1. The Grade 2 standard. Let's establish our foundational baseline here.
Now, you might hear the term commercially pure or unalloyed and instinctively think, oh, it must be soft or weak, but in the titanium world, that's not the case at all. Commercially pure, or CP2, simply means it's our industry standard baseline. It hasn't been heavily mixed with other metals like aluminum or vanadium. Instead, it just relies on its natural elemental properties to hit this incredible sweet spot. It's strong enough for heavy-duty structural use, but it still gives you excellent weldability, formability, and of course, that legendary titanium corrosion resistance.
Moving right along to Section 2, Key Technical Specifications. For the engineers with us today, let's talk mechanical limits.
The crucial number you need to remember here is 345 megapascals. That is the minimum tensile strength of Grade 2 according to the strict ASTM B265 standard. When you're out there designing a pressure vessel or a critical airframe component, this is your baseline for structural integrity. It basically guarantees the material can take some serious stretching and pulling forces before it fails. And honestly, for an unalloyed metal, that is a remarkable characteristic.
And when we look at the wider mechanical profile, you've got a minimum yield strength of 275 MPa, meaning it bounces back to its original shape even under massive loads. The minimum elongation of 20%, that means it won't just crack when you try to bend it. But the real game changer here is that density figure, 4.51 grams per cubic centimeter. Why is that a big deal? Because it's literally about half the density of steel. So when you combine that 345 MPa tensile strength with this super low density, you get an exceptional strength-to-weight ratio. You're getting serious structural integrity, but without the heavyweight penalty. And get this, another staggering figure is its extreme melting point, 1,668 degrees Celsius. I mean, wow. While you're obviously not using it at those crazy temperatures in everyday mechanical applications, this extraordinarily high melting point really speaks to the atomic stability of the metal. It makes it incredibly reliable in high-temperature industrial processing environments.
So let's zoom out for a second. How exactly does a pure metal achieve such precise mechanical properties? Well, it's all about controlling the trace elements. It's like a highly specific recipe. The key players are oxygen, capped at 0.25%, and iron, capped at 0.30%. You see, in titanium metallurgy, oxygen actually acts as a strengthener. By carefully capping these elements at these exact maximums, manufacturers can precisely dial in the strength and formability. Allow too much oxygen, and it gets brittle. Too little, it's too soft. Grade 2 is that perfectly calibrated middle ground.
All right, on to Section 3, Material Grade Comparisons. Let's see how Grade 2 stacks up against the alternatives.
When you compare tensile strength across the different grades, it becomes totally obvious why Grade 2 is the industry standard. Think about Grade 1. It sits at about 240 MPa. Then you've got Grade 5, which is a heavy-duty alloy mixed with aluminum and vanadium, coming in at a massive 895 MPa. Grade 2 sits comfortably right in the middle at 345 MPa. It perfectly bridges the gap. You get a substantial strength upgrade over Grade 1, but you don't have to jump into the harder-to-machine, way more expensive territory of Grade 5.
To put it plainly, this is exactly why procurement teams and engineers bypass Grade 1 for Grade 2 most of the time. Yes, Grade 1 has the highest ductility, which is great for extreme deep drawing, but you sacrifice a lot of strength. Grade 2 is the ultimate compromise. You gain significantly more strength for structural loads and high pressures while completely holding on to that excellent formability and that legendary corrosion resistance. It's truly the best of both worlds.
Which brings us to Section 4, Major Industrial Applications. Where's this metal actually being used out in the real world?
The applications are honestly incredibly diverse, and they map directly back to those chemical and mechanical features we were just geeking out over. In aerospace and defense, that strength-to-weight ratio is absolutely critical for airframes.
In chemical processing, it basically laughs at harsh chlorine and acids, making it perfect for reactors. For marine and offshore, Grade 2 is an absolute beast in highly corrosive seawater, which you need for desalination and subsea equipment. But it's also fully biocompatible, so medical and dental fields use it for surgical instruments and implants. It even pops up in architecture for high-end, super durable roofing.
So the main takeaway here? Unmatched versatility. It's such a wild narrative arc for a single material. Just think about it. Because of those tiny, precisely controlled trace elements like oxygen and iron, we have a metal that can literally survive for decades getting battered in subsea saltwater, and that exact same grade of metal can be safely, harmoniously integrated into the human body as a medical implant. I mean, that is the engineering power of Grade 2.
Okay, let's talk business. Section 5, UK procurement and pricing. Here is the financial bottom line for you buyers out there. The price of titanium grade 2 in the UK generally bounces between roughly 18 and 48 pounds per kilogram, and as you'd expect, the product form dictates that price. Your standard sheet and plate are usually the most economical, starting around 18 quid a kilo. But as soon as you increase that machining complexity, like making seamless tube and pipe, the processing costs naturally push that price up to the 22 to 48 range. But check out those lead times. Standard stuff like bar and rod, you can often get same-day dispatch right from domestic UK stock.
Now, beyond just the physical shape, there are some specific variables that cause market price fluctuations, and procurement teams need to track these to plan budgets effectively. Are you buying in bulk? Because larger volumes obviously unlock better pricing. What surface finish do you actually need? A standard mill finish is economical, but if you want it polished, that adds cost. Do you just need standard industrial certs, or are you looking for enhanced aerospace-grade AMS certifications? And at the end of the day, the foundation of the cost is always tied to global raw material availability, energy costs, and currency exchange rates.
So, with all those variables, how do you actually optimize your supply chain? The answer is pretty straightforward. Local, direct sourcing. Step 1, source direct. Working with a genuine manufacturer instead of a distributor instantly cuts out the middleman markups. Step 2, fast dispatch. Sourcing locally gives you immediate access to UK warehouse stock, so you dodge those brutal international shipping delays. And finally, step 3, and this is huge for the engineers, full traceability. You need total peace of mind, right? That means working with suppliers who are ISO 9001 accredited and can hand you complete mill certifications tracing right back to the original batch, proving those exact chemical properties we talked about earlier.
Which brings us to our final thought. We've seen how its perfectly balanced chemistry creates this incredible blend of strength, low density, and extreme corrosion resistance. We've seen it power literally everything from subsea platforms to surgical tools, and we've explored how direct UK sourcing makes it a no-brainer economically. Now it's over to you. Are you overspending on grade 5 alloys when you really don't need to? Or are you maybe sacrificing critical strength by relying on grade 1? Take these insights, evaluate your own supply chain, and ask yourself, is grade 2 that missing, perfectly balanced piece in your operational puzzle? Thank you so much for joining me on this explainer. Keep learning, keep optimizing, and I'll catch you next time.